Thank you, Ibrahim, and thanks to the organizers for the invitation to talk about my work today. So what I'll be doing today is talking about two works that I have done or joint works with Alessandro Bondi, who is an assistant professor at LUIS in Rome. And as the title says, I'm going to be talking about boundary attainment, or differently said, explosions for stochastic Volterra equations. So the talk will be divided in two parts. In the first part, I'll talk about Volterra equations with additive noise and explosions to infinity for kernels that are quite general. And in the second part, I'll be talking about the Feller condition, which is about explosions over intervals on the real line that are more arbitrary, so not necessarily plus or minus infinity, with dynamics that are a little bit more general in the sense that you can have a multiplicative noise, no, it's not necessarily additive noise. And however, we have to assume that kernels are a little bit more restrictive in the second part. So let me start by giving you an idea of the framework for both parts. So, okay. So we're going to assume that X, which is our process of interest, is a solution of an integral equation of convolution form, what I call a stochastic Volterra equation, which is given by initial condition x0 plus a convolution between a kernel K and some dynamics of the form Bx ds sigma x dw. And we're going to assume that this process lives in some interval, closed interval, LR, where the limits might be minus infinity and plus infinity. And it lives strictly in the interior up to some time S, which is the first time that you hit either the left boundary L or the right boundary R. So I have a solution of a stochastic Volterra equation on the random open interval 0S. So sometimes because L and R are infinity, maybe it's easier to reformulate this with finite constants. So sometimes we use sequences of approximated finite constants Ln and Rn, and we restrict X to the closed random interval 0Sn, which is the first time that I hit this approximate sequence of left and right boundaries Ln and Rn. In this case, the way I localize the dynamics of X is by multiplying by an indicator function in the integrals that I had before. But to summarize, I have X, which lives in an interval. S is the first time that I hit the boundaries of that interval. And before that time, X is a solution of an integral equation of convolution form. So the question that we have is, we want to establish necessary and sufficient conditions that would guarantee that the process X does not hit those boundaries. So in the case when K is equal to 1 and X is a solution of a stochastic differential equation, an SDE, this is known as the Feller test of explosions of stochastic diffusions. And this is precisely what we want to kind of extend. Our work can be seen as a contribution to the literature of invariance for stochastic Volterra equations. So in the paper that we did with Eduardo and Martin, now relatively long time ago, on affine Volterra processes, we discussed some results about invariance over the positive orthant RD plus, and we applied those results in particular to Volterra square root type of diffusions. In a more recent paper where we extended the theory of affine Volterra processes to polynomial Volterra processes with Eduardo, Krista, Luca, and Sara, we also had some results regarding invariance for some domains that could have some curvature, like the D-dimensional unit ball. And more recently, Aurélien Fonsi, Eduardo Abillabert, and Guillaume Sulda have obtained results regarding invariance of stochastic Volterra equations over closed convex sets for kernels that are quite general, and their Lipschitz continuity assumptions on the coefficients if they take the strong formulation, or under a weak formulation for more general dynamics. And in their works, essentially what they do is that they want to know whether a process that satisfies a stochastic Volterra equation stays within a closed convex set. And to answer the question, they approximate the equation with a pure jump process. and we establish conditions such that the pure jump process stays in the closed convex set, and by a limiting argument, they get what they want. Actually, in the first two papers that I mentioned in this slide, we also have an approximation argument because we approximate the dynamics of the Volterra equation, but by dynamics that are a little bit easier in order to get the invariance. And not only the dynamics, also the kernel can be approximated if necessary. For instance, you can approximate a kernel that is exploding at zero by kernels that are not exploding at zero, for which things are a little bit easier. So the reason why I'm saying all of this is because all of these arguments to get invariance in these papers are based on the fact that you take a limit and hence are bound to work only when the domain where you want to get your invariance result is closed. So when you talk about explosions, or what I was mentioning before, the attainment of the boundaries L and R, this is an invariance result on the open interval and hence on an open set. And our contribution can be seen as an invariance result over open intervals. Everything is restricted to a one-dimensional case. Maybe I say something related to a multidimensional setting at the end of the presentation, but this restriction is the same, the restriction that you have when you talk about the failure test for SDEs. So failure test for SDEs typically is presented in one dimension. There are some extensions to multidimensional settings, but they're a little intricate, to say the least. So as I said in the beginning, my presentation is divided in two parts. In the first part, I talk about stochastic Volterra equations with additive noise. In this case, the test for explosions that we're going to be thinking about is test of explosions to infinity, which is known as the Osgood test. And we're going to be talking about kernels that are quite general. I will take the opportunity also to talk about the stability of explosion times in this setting. In the second part, I move to the setting that I was talking about before, where the interval could be any interval of the form LR. I can have multiplicative noise that is not necessarily additive, but I have to impose stronger conditions on the kernel. And in this case, we can establish a failure test for explosions. And we will see an application of this result in the particular case of the Volterra CIR process, which is essentially the one that we use a lot in mathematical finance. So let me start with the Osgood test. So what is the Osgood test for ordinary differential equations? So imagine that you have an ODE of the form x prime equal to b of x with initial condition x0. So if the drift is non-negative and continuous, we know that this ODE has a unique maximal solution up to some explosion time. And the explosion time is explicit, is actually the integral from the initial condition x0 to infinity of 1 over b. In particular, the solution explodes to infinity if and only if this integral is finite. In other words, if and only if 1 over b is integrable. So essentially, what we want to do is to extend this Osgood test to deterministic Volterra equations, and not only to deterministic Volterra equations because we want to have a noise, we want to extend it to deterministic Volterra equations where there might be some perturbation that has the taste of a noise, okay? So we want to perturb a deterministic Volterra equation with something where later on we can put the paths of some stochastic process and hence consider additive noise type of equations. The basic reference that we're going to use in the deterministic case for Volterra equations is a paper by Brunner and Yang in 2012, and I'll say some words about this paper through my presentation. So what is the setting where we're going to do things? So we're going to do everything in a deterministic setting, and afterwards we're going to apply it to an equation that has some sort of additive noise. So in this slide, I changed a little bit the notation. So u is kind of playing the role of x. So u is an unknown function that is going to be a solution of my equation, which is equal to some initial condition that now I allow to be some curve phi t. And then you have a convolution between a kernel and some dynamics. And here in the drift, I allow myself to put a time-dependent term, which is the r, rs b of us ds. And we're going to perturb this equation with a function g that is going to play later on the role of the noise. And why do I separate phi from g? Because I'm not going to make the assumptions that I make on phi on g, because g will take the form of a noise. I don't want to make the same assumptions on the two different parts. So on the parts that do not depend on g, we make some monotonicity assumptions that are classical. So we assume that phi, r, and b are continuous. They are non-decreasing. B is actually strictly increasing, and B has superlinear growth and infinity. Now, I cannot make an assumption of monotonicity on G because G later on is going to play the role of the noise. So that wouldn't make any sense. So here we got inspired by a paper by Leon and Villa in 2011, where they consider conditions on G that are related to the behavior of G at infinity. So to be more precise, so what we need is that all the way to infinity over strictly positive time windows, the minimum of G stays bounded away from minus infinity. Okay, so this is a rather mild condition. And I want to say a few words about this condition and how it is verified by some of the noises that we're going to inject as G later on. So what we have in mind for G is, for instance, something like a fractional Brownian motion. So imagine that you have a Brownian motion W. So the Riemann-Liouville formulation of fractional Brownian motion is the convolution between a kernel of the form t to the power h minus 1/2 and W. And the condition H that I just mentioned before is actually a consequence of the behavior of this WTH and infinity. And this behavior, an important part of this behavior, is what is known as the law of iterated logarithm. So you can prove that this version of fractional Brownian motion satisfies a law of iterated logarithm where the rate of divergence at infinity is of the order t to the power h square root of log of t. Okay. Now, how do you use the law of iterated logarithm? If you take a positive time window and you take the minimum of Wt plus R over that positive time window, Wt plus RH, then you can bound it from below by a term that's exactly a term that you have in your law of iterated logarithm, and a term that depends on the increments of this process WH, okay? And there is a result of Carmona, Coutin, and Monsigny, where they showed that you can control these increments at infinity uniformly in some sense, which is essentially the inequality or the statement that I have in my slide almost at the bottom. And once you control these increments, you can show that actually the lower bound of the minimum of the fractional Brownian motion over the time window 0 t bar is going to infinity. So actually what I can show in this case is that my condition H is satisfied, but in a very strong way. The lim sup of the minimum of G over time windows is going to infinity. Now, of course, if G is equal to 0, this is not going to be the case. The lim sup is just going to be 0, but that is still is true. And the condition H that I talked about before was just, I want this lim sup not to be minus infinity. Okay, so this is kind of like the idea of how we check this condition for the noise that we have in mind. Essentially, what we use is the law of iterated logarithm, and the argument can be extended to more general center Gaussian processes. So for instance, if you have a kernel, if you take the convolution between a kernel and Brownian motion, typically, if the kernel, for instance, is integrable, then you don't have a law of iterated logarithm, you just have the rate of divergence is of the order square root of log t. So in this case, you have to work a little bit harder, and you cannot use directly these results of Carmona, Coutin, Monsigny. So you have to work a little bit harder in order to establish this lim sup of the means. But there is an inequality. I don't have time to go into all of the details, but there is a nice inequality that is called the Borel-Thies inequality, one of the fundamental inequalities for Gaussian processes, that allows us to conclude that actually the lim sup of the means also goes to infinity for more general Gaussian process.
Sergio, one question.
Yes.
So you have this for h equal to 1/2 2, right? Because I mean you have the
yeah, absolutely. In the classical case for Brownian motion, the law of iterated logarithm allows us to conclude as well. Yes.
Okay. So it's okay.
So I could add a noise that is classical. Yes, of course.
Okay. Thank you.
Okay, so let me come back to what we can prove about explosions of these perturbed deterministic equations. So there are essentially two cases of the kernel that are important, and I'm going to talk about extensions and more general results in a second, but all the ideas are basically contained in these two examples. So one of the examples is an example that appears a lot in math finance recently with these rough volatility models, because One way to approximate this fractional Brownian motion, or a natural way, is by approximated by Gaussian processes where the kernel takes the form of a sum of exponentials. Okay, so you can approximate very general kernels with kernels that have this form: the sum of some exponentials minus xit and multiplied by weights mi. So in this case, if we take a sum of exponentials, what we can prove is that under our standing assumptions, there is a continuous maximal solution to the perturb equation. And if we assume something a little bit stronger, so either the initial condition has got to infinity, or actually the limb sup of the mean is infinity. So this I call H infinity. This is exactly what I was mentioning before is true for the Gaussian processes. So this we can establish for Gaussian processes. And if you cannot establish, it would also be sufficient to have an initial condition phi that is going to infinity as t goes to infinity. So under either of these hypotheses, you can prove that explosion happens if and only if 1 over b is integrable. So this is saying just that the Osgood test for when you have a kernel that is a sum of exponentials under this additional hypothesis is exactly the same one that you have for an ODE. So this is an extension of the result of Leon and Villa, where they did something similar for ODEs that are perturbed, not for Volterra perturbed equations. And a little comment: when k is equal to 1, which is the classical case when you don't have a Volterra equation, you don't need this h infinity, or you don't need this limit of phi going to infinity, because you can get around in a different way. The reason why we have to impose these conditions is because we're working for a little bit more generic kernels. So essentially, the message is that if k is a nice kernel, such as like the sum of exponentials, then the Osgood criterion for explosion remains the same than the one that you have for an ODE. Now, I want to say a few words about the proof, because just to explain to you where this hypothesis H infinity, or this explosion of phi to infinity, is playing a role. So essentially, what you do a lot is, because this is what we know how to control, is you have your perturb equation and you use comparison results in order to control it with something that is unperturbed. This is what I call DVE0, like the deterministic Volterra equation with G equal to 0. So this is the little v that I'm putting in my slide. So there are two implications. The easy implication is to show that if there is explosion of your perturb equation, then necessarily 1 over b is integrable. The way you do that is you just use the fact that k is bounded. In this case, it's a sum of exponentials, so it's bounded. And then you bound somehow from below your perturbed Volterra equation by a deterministic Volterra equation with 0 perturbation. And then you can further bound by something that doesn't even have a Volterra structure, because k is bounded, meaning you can further bound it by an OD. And then you can show that the explosion of your equation implies an explosion of the related ODE, and then by the classical Osgood test, you conclude that 1 over b has to be integral. So actually, the difficult direction is the other one, when you try to show that if TE, the explosion time of your perturbed equation, is infinity, then necessarily the integral diverges. So to prove that direction, essentially what you need is some results about the unperturbed equation with 0g, which can be seen as some sort of control of the explosion time. So this is what I have in item 2. So what I'm saying is that when you have an uncontrolled Volterra equation, there are some results that we can establish that control the integral of 1 over b, starting from the initial condition phi at 0, by something related to the explosion time. So the epsilon is sort of playing the role of the explosion time, because epsilon is between 0 and the explosion time of the unperturbed equation. And here, in this type of arguments, where you have some sort of implicit bounds of the explosion times in terms of the integral of 1 over b, is where we use the fact that k is a sum of exponentials. So there is some structural thing about k that allows us to get this type of bounds. And how does the argument go? So the argument goes essentially, what you end up doing is comparing your perturbed Volterra equation, just as before, with unperturbed Volterra equations, where you change the initial condition by something of the form phi tn plus mn. And you keep doing this all the way to infinity, because you're equation is not exploding by hypothesis. So you can go all the way to infinity in the argument. And you have a sequence of comparison results with equations that have initial conditions that are given by phi Tn plus Mn, where Mn is precisely the minimum of this perturbation G over the interval 0 T bar. And thanks to the comparison results, and thanks to the implicit bound that you have for the unperturbed equation for the explosion time, which is the point 2, essentially what you end up getting is that the integral of 1 over b from this new initial condition, which is of the form phi Tn plus Mn, can be controlled from below by a strictly positive constant. So
Sergio,
if,
can I
yes,
ask you a question? Sorry, I'm interrupting because I'm missing a point. Sorry,
yes,
can I ask the question?
yes, absolutely.
So what is mi and xi? So that c you define c equal to sum of mi over xi. What are mi?
This is a bad notation. Thanks for pointing this out. The mn here is the minimum of the g. It has nothing to do with the sum of exponentials. So the sum of exponentials is disappearing in the constants. Sorry, it's a really bad notation. Thanks for pointing this out. The fact that I'm using a sum of exponentials is in the constant, in the point 2. So these are the mi's and the xi's that are in the constant in the point 2. But in the point 3, my mn is not the same m than in the point 2. Sorry, the mn in the second is the bold mn is more the minimum of g tn plus r for r between 0 and t bar.
But what is and xn? So if you go to the previous slide,
Is the weights that you have in the sum of exponentials. So k is of the
I
form
see, okay.
mi exponential, but this notation is really bad. Like you see, I'm using
Yes,
m
yes.
in two different ways, but
So
yeah,
this is, I mean, you have a structural property on K and it leads
yes,
to this bound. Okay,
yeah,
okay, I see.
yes.
Okay, but so this is only for the class of kernels that has this structure, then how do you?
Yeah. I'll say a few words about
Okay.
something. Yeah,
Okay, thank you.
how you can generalize it. And then where I was is that, yeah, this kind of argument that gives you that the integral over phi tn plus the minimum towards infinity of 1 over b is bounded from below by a positive constant, and hence my hypothesis that I had on phi and mn are such that this thing diverges to infinity. So the hypothesis is allowing me to conclude that the tails of the integral of 1 over b are bounded from below, bounded away from 0 at infinity, hence the integral diverges. So I just wanted to point out essentially that in point 3 is where you see the mn's appearing. And the reason why we want these things to diverge to infinity in some sense is because there are some lower bounds in the implicit bounds that we use for the explosion time. Of the integral that appears in the implicit bounds for the explosion time. So this is for the sum of exponentials. You can do exactly a similar argument for the fractional kernel, for instance. So in that case, what we can prove is, in this case, you can assume either, in this case, for instance, I don't need phi to go into infinity because if I assume, for instance, that the drift b stays bounded away from 0, I can use the non-integrability of k somehow to get something, some explosion. Or if I assume this hypothesis h infinity, this will be okay as well. But in this case, what the result says is that the explosion happens if and only if, and here the test changes. So it's no longer 1 over b that is appearing in the integral, but it's rather 1 over x times x divided by b to the power 1 over alpha. And if the integral of that all the way to infinity is finite, then we have explosion. So in this case, it's a similar argument. We use comparison results that are contained in the paper of Brunnen and Yang. We use a Osgood test somehow that is also contained in the paper of Brunnen and Yang for 0 perturbation, meaning when g is equal to 0. And we use implicit integral bounds on the explosion time, which are contained in a paper by Miller-Sig in 99. Okay. So how do we apply this to stochastic equation now is this is omega by omega, essentially. Now you can imagine that you have a stochastic Volterra equation where you have a kernel of, for instance, you can have a fractional kernel t to the power alpha minus 1 bxxs ds, and you add some a noise that is going to satisfy the right conditions on G. As I said before, using a law of iterate logarithm argument, you can show that this is true for fractional Brownian motion. So I could add fractional Brownian motion to my equation, and I know, for instance, that in this case, explosion happens if and only if, just as before, the integral all the way to infinity of 1 over x, x divided by b to the power 1 over alpha is finite. One of the nice things of the argument that is omega by omega, and the condition on G is independent of the conditions that you're making on the other parts of the equation, is that actually here I put the same H, or I use the same H, kind of like the same Hertz parameter in the kernel that is driving the drift and the volatility, but that's not necessary because I could add any other noise that satisfies my hypothesis H or H infinity, and this would be okay. So you could have equations where the noise is not necessarily given by the same kernel that is driving the drift part. A little bit of words about generalizations also. This is to kind of address Ibrahim's comment. So essentially all the things that I did for the sum of exponentials can be extended for bounded kernels. The only thing that I really need is, from a structural point of view, is that at infinity I should be lower bounded by some exponential. And when I'm lower bounded by some exponential, I'm okay. And you can reproduce the argument. And in this case, what you get is that explosion happens if and only if 1 over b is integrable. And this is something that you, for instance, could apply to a more general kernel, such as, for instance, a shifted kernel, when you take a strictly positive epsilon and you consider t plus epsilon to the power of alpha minus 1. The argument that we have for the fractional kernel can also be extended to related kernels like a gamma kernel. So if you multiply by an exponential the fractional kernel, so exponential of minus lambda t to the power alpha minus 1, then you can also reproduce the argument that I had for the fractional kernel. And in this case, the explosion is controlled by the integral of 1 over x, x divided by b to the power 1 over alpha. So essentially, we have a full picture, more or less, for kernels that are kind of some sort of fractional form, or bounded kernels that are lower bounded by some exponential at infinity. That tells us that when the kernel is nice, which is the second bullet point in my slide, then you have the classical Osgood test. When the kernel is kind of fractional, we have this modified type of Osgood test that involves this x divided by b to the power 1 over alpha. So this is kind of like closes the part of the Osgood test. We went a little bit further, and we also studied like stability of explosion times, and we kind of use this in a way. So it is very common, and here I come back to the same idea that I was talking about before. In mathematical finance, for instance, if you have a kernel that is fractional, you kind of, for practical reasons, it's better to approximate it with a kernel that is nicer, like a sum of exponentials. So you take kind of sequences of kernels kn that converge in some sense to a kernel k alpha, for instance, like a fractional kernel. And you can prove that the solutions of the equations with the kernels kn converge in some sense to the solutions of the equation with kernel k alpha. And of course, in this case, it would be very natural to ask whether the explosion times of your equations with kernel kn converge to the explosion times of the equation with the kernel k alpha. A consequence of what we just did, which is the Osgood test, tells us that this is bound to be false in general. Why? Because imagine that you take kernels that are bounded, lower bounded at infinity by an exponential, and then you take a drift of the form x log x. So in this case, I know that because if the kernel is nice, I can apply the Osgood test that is related to the integral of 1 over b. That integral diverges. So I know that for the process xn driven by the kernel kn, I do not have explosion. But when I look at the other test that involves the power alpha or 1 over alpha of x divided by b, then that integral actually converges. So the limiting process is actually exploded in finite time. So this clearly tells me the explosion times are not convergent, right? Despite the fact that the xn's are converging to the x in some sense. So instead of studying the convergence of the explosion times, we can study the convergence of the heating times of the approximated process xn. And this is what we call SNM. SNM is the heating time of level m of the process xn. And what we can prove is that as long as the kernels Kn have some sort of uniform uh, regularity in L2, which is the item one in the hypothesis on Kn, and as long as the Kns converge to K alpha in LP for some P that is strictly greater than 2, and if the drift is locally Lipschitz, then, and assuming that the explosion happens in the limit, then the heating times of the process Xn converge in probability to the explosion time of the limiting process. Of course, I have to take the limit in the right order. So I first have to take the limits with respect to n, and then I have to take the limits with respect to m, and I cannot exchange the limits, otherwise I would get the wrong conclusion, for which I have just shown a counterexample. In order to prove this type of convergence of results for heating times to explosion times, essentially what you use is some convergence of your process xn to x in a very strong sense. So you need some convergence of the soup in expectation, okay? And in order to get that, you have to control two parts. So one is the noise and the other part is the drift. For the control of the expected value of the soup of the differences of the noises, we use the Garcia-Rodemisch-Ramsey lemma. And then once you have that, once you've controlled the differences in soup in expectation of the noises, then you can use a Gromwell lemma, thanks to the Lipschitz continuity of B, to get that xn converges to x in soup before the heating times, of course, in expectation. And once you have this convergence in expectation of the soup, then the convergence in probability is just a simple application of Chebyshev's inequality. I mean, there is nothing too complicated.
So,
So
Sergio,
yes,
here, I mean, your convergence result is then m by m, right? If I fix a capital M, my lim sup is equal to 0. Lim is fixed for fixed m, lim sup in n should be 0.
yes, yeah.
So that will be the, okay.
No, the limit as m goes to infinity of the lim subs is going
But
to
no,
zero.
but this is, I mean, it's an m by m statement, I think. For each m, is the lim sup equal to lim sup in n equal to 0?
For each m, no, I have to take the limit when as m goes to infinity because
Ah, it's
s
because you're looking at S. Oh, yeah, yeah, yeah. So, okay. You're looking
s
at,
is the explosion time, so I have to take the
if you
limit
were to
in.
look at SM, which is the one that is
Yeah, okay, yes. In that
okay.
case, yes, indeed,
You
indeed.
are looking at S. Okay, that's it. Okay,
Yeah,
that's fine. Thank you. Thank you.
right. Thank you. Um, all right, and then just for the fun, we went even further, and so typically the reason why you use the kernels K and like something like a sum exponentials is that it is easier to simulate using Euler schemes such process. So we started saying, what happens with the Euler scheme? What about the explosions of the Euler scheme? So imagine that you take an Euler scheme with the step tau kh, where h is some bound on the step in your Euler scheme. I don't want to necessarily take a deterministic Euler scheme with the time step equal to h, but I want time steps that might be random, and I explain a second why, that I call tau, but are bounded by some constant h. And I take a discretization with an Euler scheme of my process xn. And this is what I call x hat n. So first of all, why to take random times rather than deterministic times? If I were to take deterministic times, even if xn is exploding, then if I take deterministic times, I could keep doing this forever, this Euler scheme. So this, for instance, the Euler scheme would never explode, and there would be no relationship between explosion of the Euler scheme and explosion of the equation with xn. So maybe if you want to do something intelligent that gives you a good approximation, you might want to use steps that are random. I'll say something about that in a second. Um, so what we can prove is the following. So using random steps, and as long as the scheme that you use with random steps, if it explodes, if it stops at some point, meaning that the sum of the tau kh is finite, then it should mean that your process is exploding. So it should mean that the discretization is exploding. Under this assumption, what we can prove is that, okay, this looks like a lot of limits, but essentially what we're saying is that the heating times of the Euler approximation of the xn process convergence in probability to the explosion time. Okay. Now, there are a lot of limits here. HT, because a priori I don't know whether this SNHM is finite or not. And then as before, I had to take first the lim in N and then the lim in M. But essentially what we're saying is that we can also establish convergence of the, if you take an Euler scheme to discretize your process Xn, and you think about the heating times of the Euler scheme, then you also have a convergence in probability of those heating times towards your explosion time. The proof is inspired by a paper by Alexandre Richard, Chalut, Tan, and Yang, where they studied the discretization, the Euler scheme discretization of Volterra equations. The only difference is that in their paper, they had a fixed deterministic time steps. So here we're using random times tau kh. The main idea is to see the discretized equation as a convolution equation where the kernel now is of non-convolution type, it's of sort of some sort of projection, and the drift is some or the coefficients are somehow time dependent. Okay, but the idea is similar. The same, it's essentially the same. You just have to work a little bit more because you have these random times that are appearing. So the kernel, when you do this interpretation, is actually a random kernel. In an ongoing work with some collaborators in Chile, in particular Soledad Torres, where we're studying like one natural way to approximate an explosion time in view of the Osgood test is, for instance, to take steps of the form h divided by b, in some sense. And this is called the adaptive scheme. And for the adaptive scheme, you can actually prove that the conditions that I talked about before are true. And you can actually prove some rate of divergence of the approximated xn that is interesting and kind of justifies that this kind of discretization scheme gives you a good approximation of the explosion types. So this is for the first part of my presentation. I'm going to check the time. So this is kind of like what we have about the Osgood test. And now I switch gears and I pass to the Feller test, okay? So in the Feller test, as a reminder, we have a solution of the stochastic Volterra equation over an interval LR. S is going to be the first time that I hit L or R. So here I'm not talking about, in my previous part, L was minus infinity, R was plus infinity. I was talking about explosions to infinity. Here, L and R are more arbitrary. And secondly, sigma is not a constant, so I'm not talking about additive noise, I'm talking about sigma x dws. So I cannot use kind of these deterministic arguments sort of in some sense, a priori. So I want to start with an example to illustrate what happens, what should happen. And this is going to be important to kind of make you understand the intuition of what is happening in the general case. So when we talk about the Feller test for explosions, and we are in math finance, what you hear all the time is applied to this CIR process that we typically, for instance, use for volatility in the Heston model. So we know that in this case, this equation has a global solution, so I never explode to infinity, but I know that the x is greater than or equal than 0. So the only possible explosion that you have is to 0. And you know that x stays strictly positive, meaning that x does not explode to 0 if and only if 2 kappa theta is greater than or equal than sigma squared. So this is the Feller test for the CIR process that we are all aware of. So let's see what will happen if I take a Volterra equation and I take the simplest one of them. So what is the simplest Volterra equation that you can imagine is the one where the kernel is an exponential. So I take an exponential kernel, the form a exponential of minus b times the time. And what is nice about this Volterra equation is that x takes Markovian in this setting, and I can write an SDE for x. So I can write this integral equation in differential form. The only thing that I have to do is to take the dynamics of the CIR process, kappa theta minus x dt plus sigma square root of x dw, I multiply by a, and the exponential, what it's doing is adding a mean reversion term, which is of the form minus b xt minus x0. So in particular, I have a dependence in the drift on the initial condition x0. But I'm back in the position when I can exactly use the Feller test for the classical CIR process because I have a CIR type of diffusion. And in this case, if I apply my test, the test will tell me that x stays positive if and only if 2 kappa theta is greater than or equal than a. Now, sigma squared has to be multiplied by a, which by the way is equal to k at 0. And then I have a term that depends on x0, which is also very important and you're going to see later. So I have minus 2x0 that multiplies the ratio between b and a. And another comment, b is minus k prime at 0 divided by k0. So you kind of have the feeling that you see it already here, that in the Feller condition for a Volterra equation, first of all, the x0 might be playing a role. And second of all, this behavior of k at 0, like k at 0 and k prime at 0, should be relevant. As we will say later, essentially what we're trying to do is generalize this to more general dynamics and to more general kernels, okay? So what do we have to assume on the kernel? And this is going to be clear in a second why we make this assumption. So here I'm way more restrictive than when I was doing in the first part. I assume that the kernel is actually differentiable all the way to 0. The derivative, so it's a nice kernel that doesn't explode at 0. So fractional kernel is out of my picture. K prime is of bounded variation. And most importantly, and this is the tool, actually, this is the message that I want to convey, is like there is a tool of convolution equations that is quite fundamental in order to get things. That is what is called the resolvent of the first kind. So the resolvent of the first kind is a non-negative measure L that is a solution of the equation of the identity K convolution with L is identically equal to 1. And this L is going to be fundamental in the Feller test, okay? The other thing that is going to be fundamental is the behavior of a function K prime convolution with L. And for reasons that are going to become more clear in 1 second, I need to assume some monotonicity on this function. K prime convolution with L has to be non-decreasing. And later on, I'll tell you why. We also want it to be bounded above on R infinity. So this seem to be rather abstract, but these are conditions that are satisfied by completely monotone kernels, like the sum of exponential kernel. And this is a particular example of a case where we can apply our results. So why do we care about this hypothesis on K? Because under this hypothesis, we can rewrite our Volterra equation as a stochastic differential equation with a path-dependent drift. So here I'm going to be stopping my process at the first time that I touch Ln or Rn, my approximated sequence of the left and right limits. And then I have a part that only depends on x at time t. This is kind of like what I would be calling the Markovian part. So there is the b dt and the sigma dw that get multiplied by k0. And then there is a term of the form plus k prime at 0 divided by k0 times x minus x0, xt minus x0. This is, if you just read the first line, that's exactly, in the case of the exponential kernel, that is exactly what I wrote before. The dynamics of x would be given by the first line, and that's all. In the more general case, when the kernel is a little bit more general, but you still have this tool L to do things, you can prove that there is, in the dynamics of x, there is the appearance of a path-dependent drift term, which is the one in the second line of the equation. So the path-dependent drift is the convolution between the trajectory of x up to t minus x0 and the measure induced by this function k prime L. So here you see that the k prime L is important. That is what is driving the path-dependent drift. For reasons that are going to become clear in a second, I want this to have a sign in a way. So I want this measure to be signed. Hence, I assume some monotonicity on k prime L. But once I'm at this point, the advantage is that I have a formulation with an SDE for which I can apply Ito's formula. The
Sergio,
path, yes,
another question. Sorry, I
yeah,
ask another question. Why
yeah.
isn't there a diffusive term in the second line?
Why there is no diffusion term in the second line?
Yes. Because it looks like the first part of the first line and this second line, they go together, which is like
Yeah, yeah.
some
It's
sort of an
essentially when you look at this equation, just imagine heuristically you're taking differential of this.
yeah,
So one differential comes from the evaluation of the stochastic integral at t.
yeah.
So that's where the K0 BDS and K0 sigma dW come from. But
Yeah.
then the other derivation is when you differentiate the kernel with respect to time,
Ah, okay.
and that only has a dt term,
Yeah,
and that's the
yes.
complicated term.
Thank you.
But it's only
Thank you very
dt
much.
because it's kind of like the derivative of this with respect to time. I don't know if I'm making myself clear.
Yes, it is completely clear. Yeah.
Okay.
Thank you. There's, I
Yeah.
mean, yeah. Thank you.
All right. So to summarize, I've written my stochastic Volterra equation in differential form with a now the Markovian part, I summarize things and I call B tilde all the part that I have in the Markovian drift and sigma tilde all the part that I have in the Markovian volatility. And I leave my path dependent term trajectory of x up to t minus x0 convoluted with the measure induced by k prime L. Now, if the second line of the equation was not there, I could apply the Feller test to the diffusion with drift B tilde and volatility sigma tilde. I remind you, the Feller test needs some hypotheses on the coefficients, and here the hypotheses that we make are exactly the same ones that you do in that you make in the classical Feller test. So I need sigma tilde not to vanish on the open interval I, and I need 1 divided by sigma square, sigma tilde square, and B tilde divided by sigma tilde square to be locally integrable over the open interval. Okay. So now the question is, how am I going to deal with this path dependent term? And this is kind of like the main message that I want to convey. So the trick that we do is we shift our drift B tilde by some constants, okay? So we're going to take a parameter C that is not going to be important in the test. That is an arbitrary constant in the open interval. And we're going to do some shifts depending on whether I'm at the left of C or at the right of C. So at the left of C, I'm going to shift my drift by a beta and at the right by gamma, both constants multiplied by a common constant, which depends precisely on K prime L. So it's going to be exactly the gap between K prime L at 0 and K prime L at infinity. So here I'm using the K prime L is bounded from above. So this K prime L at infinity is actually a constant, okay? K prime L is monotone. So this is precisely kind of like the range of K prime L going from 0 to infinity. And these type of constants are the ones, and these shifts are the ones that are going to allow us to handle the sign of the path dependent part. And in order to use, instead of martingale kind of arguments, sub-martingale or super-martingale arguments to prove what we want to prove. So from this point onwards, I'm not going to do the proof, but from this point onwards, essentially we just define, like in the classical case, we define a scale function, which I call P, just as in the classical case, except that I define it for shifted kernels, shifted drifts, B tilde, and the modified volatility sigma tilde. And I define the auxiliary map V, that is going to be the one for which I apply the test, that is defined in terms of the derivative of the scale function. So just as a reminder, in the classical case, for instance, when k is equal to 1, this is the k prime is equal to 0, there is no shift. P is the classical scale function. In that case, what happens is when you apply P to X, you get a martingale. And when you multiply V by an exponential, you get also a sub-martingale or a super-martingale. And this is kind of martingale arguments are the ones that allow you to prove what you want to prove about the explosion time. Okay? So essentially what we do is we shift the drift and then we apply similar arguments that in the classical case, controlling the sign of the path-dependent part with this auxiliary function. And what we can prove is the following. So there is a necessary condition, and then there is a sufficient condition. And as I anticipate now, I'm telling you in advance, they are not equivalent. I'm sorry. So for the necessary condition, we have the following. So suppose that we concentrate on the left limit. So I call the first time that I touch the left limit S minus. So one necessary condition for never touching the left limit is that V, this auxiliary function, explodes to infinity as I approach the left limit, as long as I use shifts of the drift that are negative. And for the right limit, I have something similar. The necessary condition is that V has to explode to infinity at R, as long as I take shifts that are positive. If I combine the two, essentially the condition that I need, that is necessary for no explosion, so not touching either R or L, is that V has to explode to infinity at L, V has to explode to infinity at R, but for the limit in L, I have to shifts that are negative, and for limit in R, I have to use shifts that are positive. Okay? So this is the necessary condition. Now, for the sufficient condition, because we're going to take shifts that depend on L and L and R could be infinite, I have to formulate things in terms of the L ends and the R ends. But if you forget about the fact, if you imagine that L and R are finite, essentially what I'm doing is now I'm shifting the auxiliary function V or the test function V by x0 minus L at the left and by x0 minus R at the right. And what I need is the following. So a sufficient condition for never touching the left limit and the right limit is that V explodes to infinity at L when I shift with x0 minus L and at R when I shift by x0 minus R. And here you notice that this condition is completely incompatible with the one that I said before, because in this condition, at the left limit, I'm using a shift that is positive because x0 minus L is positive. And a moment ago, the shifts that I was using for the limit at L were negative. And the same thing for R. Here, the shift for R is negative, but the shifts that I was using for the necessary condition were positive. So we have a gap between the two. The two are not equivalent. What's happening in the exponential kernel case is that in the exponential kernel case, and allow me to go back, the exponential kernel case is such that this k prime convolution with L is a constant. So there is no gap. So this constant is equal to 0. Nothing depends on the shifts. So the moment that you erase the dependence of your auxiliary function with respect to the shifts, you have an equivalence and you have the classical failure test. Okay. Of course, the classical failure test for the modified drift B tilde and for the modified volatility sigma z. Now, to finish my presentation, how much time do you have, Ibrahim?
2 minutes.
Okay. To finish my presentation, I want to tell you what happens when you apply these results to the Volterra CIR process. So in this case, you have a kernel K and you have your dynamics kappa minus theta x ds and square root of x dw. We know that there is a strong solution to this equation thanks to a result of Eduardo and Omar. So the only possible explosion is to 0, and we want to know whether you explode to 0 or not. I should say that there are recent results, and this is something that I added to my slides today, like a few minutes ago, because there are two papers that appeared a few days ago where they go a little bit beyond what I'm saying in this particular case. So have a look at those papers because they are very new and they say more than what I'm going to say. So they actually extend, for instance, results to explosive kernels like the fractional kernel. But let me tell you what our results tell us. So in this case, the idea is to apply the failure test. So I have to compute my scale function, the derivative of the scale function. I have to define my auxiliary function, V, and I have to upper and lower bound it in order to know whether it explodes at L or at R, and that's it. But the conclusion that I get is the following. So the conclusion is that a necessary condition for never touching 0 is that 2 kappa theta has to be greater than or equal than k0 that multiplies sigma squared plus 2x0 k prime L at 0 divided by k0. By the way, k prime L at 0 is k prime at 0 divided by k0. So this is exactly, if you read this first line, the condition that I have there for 2 kappa theta being bounded from below is exactly what I had in my example with exponential kernel. Okay. Now, for the sufficient condition, I have something very similar, except that instead of k prime convolution with L at 0, I have k prime convolution with L at infinity. And this is precisely the gap that I have between the two. So I cannot close the gap. There is a gap between the sufficient and necessary conditions that is given in terms of this gap between k prime convolution with L at 0 and k prime convolution with L at infinity. By the way, k prime convolution with L and infinity for a completely monotone kernel, you can compute it explicitly as minus k at 0 divided by the norm of k between 0 and infinity. Would you give me 1 minute to say something? So essentially, we can apply these results to the sum of exponentials, okay? And we did it. And we showed that in some cases for certain parametrizations that have been used in the literature, you actually touch 0. This is more like for the sum of exponential kernel, there is a different way to see the Volterra equation this maybe you have heard as a multi-factor kind of representation, when you see the process X as a weighted sum of processes yn that solve an SDE in dimension n. So in this case, for instance, if you want to study explosions to infinity of X, it's like studying explosions to infinity of this SDE in n dimensions. And for the SDE in n dimensions, you have criteria. We actually did it. We had to extend a little bit some results that appear in the literature to show what those criteria could be. in our setting, but essentially it's criteria of, for instance, there is something called the Kashminsky type of criterion. And my point being is that when you study SDEs in multiple dimensions, you have a gap between necessary and sufficient conditions. Hence, our cap is not surprising. And when you look at this way, you realize that maybe in this particular case, our formulation with the resolvent of the first kind, L, is more convenient than the formulation as a multidimensional SDE. I have finished, so these are the two works that I presented. One is a preprint, and the other one should be appearing soon. The one about the Osgood-type, which was the first part. Thank you, Ibrahim, and everyone.
Thank you, thank you, thank you to you. Great talk. There are several questions on the chat. If you want to choose one of them and answer, because we are almost out of time, they're
Okay.
up to you.
Should I look myself? One second.
Yeah, I mean, they are all.
I don't see anything. Is that normal?
Q&A. There's a Q&A part. You want, I can
Sorry.
choose. Yeah.
There's a Q&A part. Um,
Yeah, I mean, the first question is for a drift.
yeah, I see it, the Q&A. Sorry.
For a drift that grows like x log x, the classical Osgood condition says no explosion, but your fractional kernel condition predicts explosion. Why does fractional memory accelerate explosion so drastically?
I have no intuition whatsoever about what's happening there.
Okay.
So that's a good question, but I have no intuition. Of course, you can imagine, it's easy to imagine like processes that are not exploding that convert to something that explodes, right?
Yeah.
But why this x log x is important, I have no idea. It's a good question. I have no intuition. I don't know what to say. It's purely computational for me, but I don't know. I have no intuition of why the kernel is doing this.
Okay. And also, I have one question too. In your Osgood tests, right, in the beginning, the what happens inside compact domains of your domain shouldn't matter, right? So, I mean, you should have some general diffusions, general dynamics inside the compact set of your domain, and then what should only matter? The tails, right? Do you have any statement in this regard? Like,
I didn't understand. Sorry, can you repeat it,
so if you go
Ibrahim?
to your I mean, you want to measure explosions, right?
Yes.
And you at the beginning you always argue by by comparison, right? By signs of drift and this kind of things, your derivative. So if you
Hmm.
do this kind of things on, right, you look at LR, right? Whatever
Yeah.
your dynamics here shouldn't matter. I mean, only the tails should matter, right? Is there any statement in this regard? So if I
Uh,
have one general
right.
term with two
Um,
terms, right? They are not far from each other inside, and they are in
mm,
fact equal on the tails. They should have the
right.
same number. Do you have?
Yeah. Uh,
Is this intuition correct at least?
I don't know. The question is that intuition correct in the case of the regular classical SDEs? Don't
Or
know
even
if,
ODs?
or even know these. Um, hmm. I don't know. I feel like these test functions that you use again in Osgood or in Feller, kind of you're using the behavior of the coefficients over the whole interval, right? So I don't know if
I see.
you can localize these things. I don't know if this is answering your question. When you define these test functions and everything, everything depends on the whole. They're integrals over the whole domain in some
But
sense.
I mean, your exit should only matter at the tails, right? The explosion.
Yes.
If there is no statement like that, okay. That was just a question on that regard.
Mhm.
We are anyway out of time. I'm gonna
Right.
stop the recording.
Okay.
And thank you to you. Thank you for this
No,
great
no,
talk.
thanks for the invitation. Thank you for the opportunity.